opportunities for well intervention so that it can produce more. So those are key responsibilities of the production technologist. So having said that, I would like us to move to the core concepts. So the reservoir has fluid, right? And if the fluid remains in the reservoir, let's say the reservoir is not good enough, there's no interconnectivity, permeability. So it means it cannot deliver fluid into the wellbore, right? So it is important that even when as we have fluid in the reservoir, we should be able to deliver it into the wellbore. So that relationship, that inflow performance relationship curve that you are seeing on the screen defines what the reservoir can deliver to the wellbore, right? What can flow into the wellbore. And it is actually a relationship between the flow rate of the well and the flowing bottom hole pressure, which we are calling PWF. What are the things that actually determine what flows into the wellbore? That is the inflow. You are looking at the reservoir pressure. If your reservoir pressure depletes, then you won't be able to flow into the wellbore, or you just flow a minimal amount of fluid into the wellbore. If the permeability, the higher the permeability, the higher the amount of fluid that you can flow into the wellbore. Then we're also looking at things like fluid properties. For instance, a highly viscous reservoir makes inflow very difficult, right? You're also looking at solution gas. So those are the things that you are looking at in fluid properties. Then another thing you are looking at is skin. This skin, mind you, skin is not just about formation damage. It's also about how you even drill the well, like partial penetration, for instance. Then limited entry, maybe you didn't perforate the enough interval. So those are things that also contribute to skin. Then the chief of them is formation damage. Fines migrate as you are producing and plug the interconnectivity, the pore spaces and their interconnectivities, thereby reducing the permeability near the wellbore. So you may need to stimulate it. So all those things affect how much fluid goes into your wellbore, right? So this is, so if you look at, as we will see later, we'll see that to improve these inflow performance relationships, we are looking at managing all these parameters to make sure that we have enough fluid in our wellbore. Then the next thing, after the fluid has come into the wellbore, how do I lift it to the surface? That is what your vertical lift performance curve is talking about. How do I move the fluid that has now flown from the reservoir into the wellbore to the surface? Because if it doesn't get to the surface, I will not have any production, and I'm not in business because I will not make money, right? So it represents, so the fluid vertical lift performance curve is trying to calculate the pressure drops as you moved your fluid from the wellbore to the surface. That is what we are looking at. And what are the things that you look at that govern that vertical lift performance? First of all, you are looking at your tubing size. That is why when you are completing a well, selecting the appropriate tubing size is very important, right? If you select a very small tubing in terms of diameter, you are going to have a lot of losses due to friction, right? Then if you select a very large one, your reservoir pressure may not, your fluid velocity may not be enough to push the fluid to the surface. So that is why at times you see well interventions where you go there, the fluid for that particular well is too large, the tubing for that particular well is too large, so you go with a smaller tubing that we sometimes call velocity string. Then the other parameters that determine this your vertical lift performance include your gas oil ratio, right? So dissolved gas in the fluid. Some fluids don't have enough of it. So there is something we call solution gas oil ratio. That is the gas that is dissolved in the oil at reservoir condition. So as you drop the pressure, gas will be liberated. So if you don't have enough gas dissolved in that oil, that means your solution gas is very low. So if you see fluid property where the RSI, as we call it, is very low, that is telling you that you may not be able to produce more. The lift will be a bit difficult. Then water also causes problem for us. You know, water is heavy. The density of water is higher than that of oil. So as water is increasing in the wellbore, then the overall density of the fluid stream is increasing. So you need more energy to move it from the wellbore to the surface. Then your wellhead pressure is like a load. You need to overcome it for you to be able to produce into your separator. So if it is too high, then it will also limit how much you can lift to the surface. Then your pressure losses, like I said, your tubing size will cause a lot of friction. And even when the gas that we talked about is even so much, if it increases so much, then it is going to cause a higher pressure drop due to friction. Because if you look at the vertical lift performance equation, you see that the pressure drop due to friction increases, varies directly as the square of velocity. So as your velocity is increasing, maybe you are in a gas lifting, your gas lift system has too much gas. Then a time will come where instead of the gas helping your fluid, lightening it and helping you to lift it to the surface, then the pressure drop because of the increase in velocity as we are injecting more gas now overcomes the advantage you are getting in reducing the density of the fluid. So you need to be careful with that. So all those pressure drop and even restrictions on your tubing. For instance, if you have a wax buildup on your tubing, it's going to create a restriction and that will cause further pressure drop. So all those are the items that we need to manage as we are producing. So this slide couples both the inflow and outflow. This is the entire system now, the inflow, outflow. And where you have the intersection of the inflow performance relationship curve and the vertical lift performance curve is the operating point for this set of parameters, right? For every parameter that you use to do this calculation. So where they intersect is the operating point. Remember, the operating point is not exactly the optimum point, right? So you have to know that because you can use a very high, you can use set of parameters and calculate. At the end of the day, you pull in water or you pull in sand, you pull in unwanted fluid, right? So your rate is high, but that is not the optimum. The optimum is where you need to balance what you are producing with the unwanted elements that you are producing, like sand, water, and gas, right? So this is the operating point for this set of parameters, but note that it may not be the optimum point. So what we do is we do what we call nodal analysis in order to analyze production system. So nodal analysis is just like analyzing the pressure drops along the line, right? So what you do, choose a particular point. Sometimes we can choose wellhead. Sometimes, most times, we choose top of perforation. So we choose that as a point to do our analysis. So what do? We look at from the reservoir up to that point. That is the inflow, right? Then we look at from that point to surface. That is the outflow. So where those two curves meet, the IPR becomes equal to the VLP. So at that point, the flowing bottom hole pressure from the reservoir up to that point and from that point to the surface will be equal. And the inflow in terms of PWF will be reservoir pressure minus pressure drop from reservoir up to that point. Then the vertical lift performance will be the PWF at that point also will now be the loss
Sorry. Hello, Mr. Hyacinth. You're freezing up.
So at that point, those two pressures are equal, so we can equate them. And since we have reservoir pressure and we have the end point pressure, maybe wellhead or separator pressure drops along the line. So that analysis. And if you look what we do, our key job, try and make the optimum rate for the, yes. Oh, sorry. Hello, can you hear me now? Let me even check whether
Well,
I'm
I
still
wasn't sure
connected.
if it was me or you. I think your network is breaking up because I
Maybe
checked.
network.
Yeah.
Oh, okay.
So you were
But can you hear me
cracking up
now?
a bit. Yes, it's better now. It's better now.
Is it better now? Okay.
Yes.
Okay. Sorry about that. Can you still see my screen? Am I still sharing my
Yes.
screen?
Yes,
Okay.
yes. But you've left
Thank you.
presentation
So
mode.
I'll just put it in a presentation mode back.
Okay, thank you.
Okay. Okay. So if you can hear me, please, whenever there is an issue, just let me know, please. Thank you. Okay, so in terms of production optimization, what are we trying to do? These two curves, we are looking at them. And in terms of the inflow performance curve, we are trying to move it as far to the right as possible, right? So what do we do? What are the things that we actually do to move it to the right? We look at things like stimulation. For instance, that will help us move it to the right, because inflow, anything that will help you increase inflow, flow from the reservoir into the wellbore is helping you move it to the right. Then in terms of the vertical lift performance, anything that will help you move it downward. For instance, if you gas lift is helping you move it down a bit. That will also help you increase your rate. So those are the things that we are actually doing in terms of production performance optimization. Okay, so can you still hear me, please? Please confirm you can hear me.
Yes, yes, we can.
Okay. Okay. So having looked at those basic concepts, for us to even talk about production, we need to have it well in place. So like I said, one of the key areas that the production technologists contribute to the company is well completions, conceptual well design, right? So in terms of completing a well, we can complete a well as open hole. That gives us maximum inflow because we now have a large portion of the sand face exposed to the well bore, right? So that helps us a lot. But we cannot do that in an unconsolidated formation. Then we also have case tool. cased and perforated. We can have casing, we can have slotted liner or cemented liner, cemented and perforated, right? So that is also good because it now helps us in consolidated formation, but that reduces the area of the reservoir, the surface of the reservoir that we are exposing to flow. So you need to think about those when you are designing your well. Then there is one element that is very important, and that is sand control. So sand control, because if you complete your well and you produce a lot of sand, like last year, 2 years ago, it's more than 2 years now, one of the organizations completed a well and it flowed for like 6 months, right? After 6 months, they started producing a lot of sand, and the sand eroded all the tubing accessories. So they had to do a remedial sand control. So that costs a lot of money too. So you need to think about your sand control method when you have a lot of money in the future. We'll talk more about the sand control because of its importance. But before then, so you have lower completion and upper completion, like I said. So your lower completion is all those your sand phase. So you are looking at sand control, you are looking at perforation. Those are the things that you are looking at when you are designing your lower completion. Then the upper completions, you are looking at tubing and the accessories. So for every well, you need your tubing, you need some accessories, you need all those packer, you need a way of circulation, you need a sliding side door for circulation. Then you may also need mandrels to enable you install your gas lift valves. So these are some components that you need. You don't need them in every well. So what you are going to choose to complete a particular well depends on the requirements that the functionalities that you're expecting from that well, and also the thought of future well intervention, then economics. So you are looking at all those, right, as you are completing your well. So you can see Packer actually helps us isolate zones. Like you can see, this well was completed on 2 zones. Then you see 2 packers isolating the second zone. The first packer isolating the second zone from the first and the second zones. Then the upper packer is actually protecting your tubing, your casing, that from rust and fluid from the reservoir. So all these accessories, like I said, it's not all of them that you need for all the wells all the time. It depends on the functionalities that you want, right? So I will just pause for a moment and ask us the ones that we think are the mandatory ones. Somebody can just raise his hand. The ones that you must have in all your completions. If you can help us with that. I'm trying to see the hands that may be up. Or somebody can just unmute quickly and just mention the ones that we need in all our wells. A few of them, please. Can somebody do that for us?
Zemefeta, if I pronounced that correctly. Please, you can go ahead.
Yeah, you tried. So the ones I think that are very important, we have the packers, which is very important. We have the sliding slip doors, very important. We have the SSB, city valves, very important. We have flow completes, very important. And we have nipple in case of interventions and the rest, very important as well. Yeah, I think that should be sliding slip ends. And the side pocket mandrel is important if we were to go into like artificial lift method, like to inject gas into the well. If there's possibilities for that, so that's very important as well. Thanks.
All right. Thank you so much. I like that. Thank you. So it's not all of them that you need all the time. It depends on the functionalities that you are looking at. Thank you. Okay, so because of sand, I will not dwell so much on this. So like I said, sand production can cost you a lot of money, right? So pay attention to it when you are completing your well. Even when you are producing, please pay attention to it. We do wellhead sampling like twice in a month, right? Just to make sure that we are monitoring sand production from our wells. Because if we produce sand, it's going to cost us a lot of money. So when you are designing your well for the first time, this could be a guide on selecting the appropriate sand completion, sand control equipment, right? So if you look at the chart at the top, this is actually particle size distribution chart, right? So you get the data for this particular chart from what sieve analysis. Your geologist will do this for you and give you the results. So what you just need to plot is cumulative percentage weight on vertical axis, and also this particle size on the horizontal axis. So on those percentage, you read off 10%, you read off 50, you read off 40, you read off 90, read off 95, right? So those fractions will now give you your sorting coefficient and uniformity coefficient. So by the way, it's not every formation that needs a sand control mechanism. If a formation is consolidated and you've also produced from that reservoir and you've seen that you didn't produce so much sand, right? But most times you won't have that information. But just know that when your formation is consolidated, you may not need sand control mechanism. And how do you check that? You have rule of thumb. So you look at, is the formation deeper than 10,000 feet subsea? The depth of the formation. Then you also look at your sonic log transit time. Is it less than 90 microseconds per foot? So if you combine those two information, you can decide that, okay, let me complete this well without a sand control mechanism. But where you need it, then you need all those uniformity coefficient and the different percentiles that I've displayed here to choose the kind of sand control mechanism that you are going to use. So you can use standalone, depending on this analysis. You can use premium screens. You can use gravel pack. You can use open hole gravel pack, frac and pack and co, depending on the outcome of your analysis. You also use this particle size distribution data to design those sand control mechanisms. Yeah, so maybe another section may help us deal with all this, but I just brought it because of the importance of sand control in your completions. Yeah, so the other things, just like we've discussed, you are looking at gas lift. Some wells initially may not need a gas lift, right? Because maybe the RSI is high and the viscosity is low, right? But as you start producing more water, like I said, as you start producing more water, the density, the average density of your fluid stream, the density of your fluid stream becomes too heavy for your natural energy from the reservoir to lift. So you may need gas lift at the end. So when you complete your well, even if you don't really need gas lifting the well, I think it's a good practice to install, to add gas lift mandrels to your design, even if you dummy them out and use them in the future. Then, so artificial lifts is actually made up of two main categories. So you have your gas lift, then you have your pumps. Pumps could be progressive cavity pump. It could be electric submersible pump, ESP. It could be rod pump. It could be hydraulic. So those are the two basic artificial lifts, gas lift and pumps, the various types of pump. Gas lift actually lightens the column of your fluid. So it's working at density, reducing the density of the fluid column so that it will be lighter to lift to the surface, right? While pump is actually increasing the pressure of the fluid stream. So it's adding the pressure that you don't have to the system. Yeah. Okay. So having said all this, I want us to understand, to know that whether you are drilling a new well or you are maturing a well intervention opportunity, it is a team effort. It is not one discipline or one person's effort. So the disciplines that actually help us, I'm sure you've taken presentations from most of them, are the geosciences. And when I say geosciences here, I'm looking at the geologist and the petrophysicist, right? So they help us, they tell us what is down there in the reservoir before we even think of drilling. What are the properties of the rock? You know, they help us with all those maps, structural map, for instance, right? So where I'm drilling, am I drilling on a flank where once I start producing, water will come in? Then what kind of depositional environment, like surface, channel sand? If you have surface, you'll be happy, right? So they help you with all those ones, quality of the sand. Then the reservoir engineer is looking at, will fluid even flow in the first place? So he's looking at defining the IPR, looking at fluid properties. Do we have high viscosity fluid? Then looking at drainage strategies, doing his dynamic model to make sure that everything is cool. Even when we do intervention, for instance, you see the PG looking at maps, looking at the quality of the sand, right? Looking at the quality of the sand. You see the PP looking at these fluid contacts, right? The wells that produced around there, when did we acquire saturation log last, right? What is the current oil water contact? Is looking at all those so that we don't perforate into water. Even when we are perforating, is also in the field, making sure that we do proper correlation and make sure that we don't perforate at wrong intervals. So they contribute a lot. Then if we are looking at a new well, and like I also said, for big organizations, the well engineers actually do the well intervention. They carry out the well intervention themselves, right? So they are looking at constructing the well, providing all the physical hardware and the constraints for designs. Those are their contributions. Then the facilities guys, do we even still have ullage? Do we have more capacity to handle the additional oil that we are going to produce, or gas, right? So they are looking at all those. So the PT interfaces with all of them to make sure that the job is done. Thank you. So in terms of opportunity identification and maturation, this is like a flow chart, a process of maturing opportunity. So the first thing is to we gather data, right? Well test, pressure data, all those BHP data, right? Production data, historical production, petrophysical logs. Like I said, you are checking contacts. What are the present contacts? The wells that produced around there, how did they do? What is the current BS&W? How did the water come in? When you are looking at the map, are the wells in a particular part of the structural map the high water producers, or are the wells at the crest? How did they perform? Did they produce water? Those are the things that you are looking at. So you are looking at well history. Well history, I made it bold. It is very important. When you are working, make sure you ask for well files, right? Well files, digital well book. Know the history of the well. You're not knowing the history of the well can be a problem. Maybe you are planning intervention, for instance. You've looked at well performance chart, you've done all your analysis, and you've decided to go and stimulate a well. Maybe they've done that stimulation, but because you didn't read through the history, you didn't even know that they've stimulated that well, but the recipe did not work out, right? And you are using the same recipe that has been used before to go and still stimulate that well. So history is very important. And as we analyze all these data that we've gathered, we identify problems, and problems are actually opportunities, because if we solve those problems, then we can increase production. So problems like maybe the well has a very high skin, is producing a lot of water, lift is an issue. We can even identify opportunity for new drill. Like if we see bypassed pay or unswept zone, we can analyze it and say, okay, let us put an infill well there, right? Then we can also say, okay, let us complete so and so well on that particular interval. So when we see those opportunities, we now do the detailed work, which involved well performance analysis, reservoir performance analysis, and modeling. Then we try and simulate the intervention process in well models and dynamic simulation models. For instance, if we are going to reperforate, which interval, all those ones, we simulate it. Then at the end of the day, we model it. Integrated production system modeling is very important, because it couples everything. You are not working with one component in isolation. So it helps you, it shows you, it gives you an idea of what you are going to produce when you couple all the production, the components of the production system. Then you also do economics at this stage, then secure your management's approval to go for this opportunity, because they are the ones that will pay for the intervention. So either JV or your own management get their buy-in, then you execute. So execution, part of it is prepare your proposal, then get a good vendor that knows what he is doing to carry out these operations for you. Then after that, you you review what was done. Did it work, right? Then you keep, if it didn't work, why? If it worked, back to step one. So that is opportunity maturation. So like I said, the problems are actually opportunities, right? Because when you get a problem, if you solve it, then you reap reward for it. So what are the common well problems? You are looking at formation damage, high water production, high gas production, sand production, wax, all these flow assurance issues, then failed completion equipment, well integrity issues, fishing hole. Last year, most of the fishing gave us a lot of additional oil, right? But when you see fishing, when they say fishing hole, you may not even know that it could add to your barrels that you are producing. That one happened to us last year, actually. Then suboptimal gas lift. You need to do gas lift valve change out. Those are the things that you are looking at. So problems actually give you opportunities. So how do we now find those problems? So what we do is we carry out well performance analysis, well and reservoir performance analysis. Is there production decline? If there is decline, why? Then we look at expected performance versus actual. Is there any gap? Based on, if you model this well, is it really giving you what the actual production is? Is the actual production significantly lower? Or your MER, your maximum efficient rate test, right? Maybe you tested that well, it gave you like 1,000 barrels of oil per day. But the actual production doesn't really add up. You know, when you test all your wells, then at the end of the day, maybe the sum of the well tests is far higher than the total production from that field. Then you start looking for bottlenecks within the surface facilities to remove them so that you can produce more. Then another thing you do is check performance of similar wells. Let's say a couple of wells were completed in the same reservoir, but one does not really produce. So you need to find out why, right? So that comparison, you are looking at gross, you are looking at net production, you are looking at water core, all those ones. So you look at it, is it significantly different from the other wells? Those are ways that you can use to identify problems. Then reservoir and wellhead pressures, very important. Your wellhead pressure can tell you a lot. For instance, if there's wax in a particular well bore, because of the buildup of wax, if you close in that well, the CITHP is going to rise to the normal value that you are expecting. But if you float that well, over time, the flowing tubing head pressure is going to start decreasing. For the same choke size, because of wax buildup within the well bore, you are going to have a lot of pressure drops that your flowing tubing head pressure will start dropping over time. So it's a sign that there's a problem. Then sand water production samples too, they tell you a lot. Like I said, we sample our wells regularly for sand, and if sand is increasing, we can say, okay, let us reduce the bin on that well. And we've seen a couple of them have drop in sand production by merely doing that, right? Then you look at your logs, your saturation logs, commonly known as, commonly called RST. RST is just a brand anyway from Schlumberger, right? Then do you need to take a production logging, right? Check CBL and all. How is, okay. Be mindful of spurious data, right? Some measurements may not be correct. So don't just take every measurement that you see, especially when it comes to things like GOR. Be careful, because GOR can rise very high, maybe because there was a significant reduction in net production of oil, right? So be careful. Then I want to quickly look at one problem, right, that is very common, which is water production. So at this point, I'll just pause and quickly ask, how does water get into our well bore? Do we know the mechanism? Anybody with an answer, please? Hello, Gerard, can you hear me? I hope
You
my
started
network
breaking
has
off
not been
when you were about to ask the question, but I think we got the question.
Oh,
So which is, how does water get into the well bore?
So sorry about that. So is it better now?
It's still breaking up a bit.
Give us a hint. Okay, sorry about that. My network is bad. Why? Okay, but can you hear me now?
Yeah, it's better now. It's better now.
Okay.
So if you'd like to answer, you
Please,
can raise your hand.
somebody should just quickly let us.
Okay, Ronami Michael, please go ahead.
Okay, thanks, sir. Sir, is it a water coning?
Exactly, that is one of them. Yeah, that is good. Yeah. Okay, so why I asked that question is, water is a big problem in the oil and gas industry. In fact, we produce more water than oil, right? And we go through a lot trying to solve the problem of water production, because water production, as you are producing more water, your oil cut, let me use that term, is dropping, right? Sure, we know that. And also, when we produce this water to the surface, we spend a lot of money handling it. Water handling costs money, right? So if you produce less water, your operating expenses will be lower. But if you want to manage water production, you need to know how the water is coming into the wellbore. It will help you in managing it. So I'll just go to the next slide. So I've talked about the first 3 bullet points. We need money to manage water, and water is always in our reservoirs. There's no way we can avoid water. right? But we can manage it. So we need to understand how it is coming so that we can apply appropriate treatment for water. So the way water coming, in some reservoirs, we use water injection to maintain reservoir pressure and also to increase sweep to the producer, from the injector to the producer, right? So if we have good sweep, let me say piston-like sweep, it may take time before we produce that water that we're injecting. But what if we have fingering? So if we look at that system, we are thinking, how long will it even take before the water we are injecting into the reservoir will get to the producer? Or are there faults in the reservoir that the water we are injecting we just ride on and go straight into the well? Then another way that water can enter your well bore is through casing or packer leaks, flow behind casing. Those are ways. Then if you complete your well too close to the oil water contact, that is the water zone, right? You are going to pull in water quickly. So water comes into your well bore through that means too. Then oil water contact movement, as you are producing out the oil. Nature does not take vacuum, right? Does not allow vacuum. So what is going to happen? Water will come in to replace that oil that you are removing from the reservoir. And at a stage, your water will rise up to your perforations. Then you've produced a lot that is only water that is left. So the zone is watered out. Classify them, like you said, into coning, natural encroachment, and channeling, right? So that is that. So how do we actually characterize that water production? How do we know what kind of water production we are doing? So we have some diagnostic plots, like this one that I'm showing you. This one is showing water cut profiles for various water production mechanism. So if you look at the first one, which is chart curve number 1, you see that as soon as we started production, water came into the well bore almost from day 1 and rose to maximum and stayed there, right? So if you see something like that, it will be casing leak. It could also be flow behind casing, right? It could be that you completed your well in water, in short. Then you can also see the profile number 2. You produced for a long time, the water came in. And in that case, you are looking at things like completion near water zone, or you fractured into water as we are doing fracturing. We don't do too much fracturing in Nigeria anyway. We don't. Then maybe after you produce for a while, your casing started leaking, you can have such a profile. Then 3 is looking like natural, natural encroachment, coning, gradual coning, right? So you see charts like this actually help you in, if you compare this with your well performance chart, then you have an idea of what it is. So for us to look at the water production mechanism, we are looking at well performance chart, we are looking at diagnostic plots. There's also CHAN, which we will see. Then we can also do saturation log to see whether the current contact has even reached our perforations. Then we can do production logging to see from each zone which fluid is being produced. Is it water? Is it oil from each of the zones? So PLT can tell us that. So like the diagnostic plot that I mentioned, CHAN plot, an SPE paper 30775. I think he did this work in 1995 or thereabout, right? So it helps us characterize how water is coming. Like if you see the charts at the top. So this chart, the way to make it is to calculate your water oil ratio. That is your water rate over your oil rate, right? That gives you your water oil ratio. Then you do the derivative of that water oil ratio. That is the water oil ratio of the current of this period minus the water oil ratio of the previous period divided by this time minus the previous time in days. So when you plot this water oil ratio and the derivative of the water oil ratio, it gives you signatures that help you characterize your water. For instance, the first chart, these are not the only chart on that paper. Please try and lay your hands on that paper so that you can also read it and understand it, because these are not the only charts there, but these are the major ones that I just said I should show. So if you look at the first chart, you see your water oil ratio staying constant for some time, then all of a sudden it starts rising. Then the derivative is what we actually use in determining whether it's sconing, whether it's channeling. Then there's when you see the paper, right? So the first chart is showing channeling. The derivative of water oil ratio goes up, right? That signifies channeling. Then the second one, you see the derivative goes down. Can you see the curve down? So that tells us that there is coning in this particular, in this well, in a well with this kind of profile. So I've also said how you can plot it. You can use Excel to do your plots when you are trying to characterize your water production from a well. You can use Excel to do the chart. You can use OFM. You can put some scripts on OFM and plot them to get the chart. So the first thing you need to do is get the production data, then calculate your water oil ratio and water oil ratio derivative, then plot them on a log-log plot, right? Plot them on a log-log plot, then it shows the profile. And from the interpretation, you can actually infer what kind of mechanism that water is coming into your well. So be careful also, when you read the paper, you'll also see that you need to be careful of noise, because sometimes it's not as clear as this, as we will see now. Okay, so I just picked a few, I just picked some examples just for you to see analysis that have been done before, right? So if you look at my screen, please confirm you can still hear me. I hope I'm not talking to myself.
Yes, we can.
Thank you. Okay, so I'm trying to rush because time, we've overstepped our time. Okay, so this particular well performance chart, you can see can you see the water production profile? It started and increased gradually, right? Can you see it? The blue curve on the first chart by your left-hand side. Yeah, so that is the water curve. You see how it started, the slope is gentle, then it rose to a high value, which if we compare with the conformance chart that I've shown before, is looking like chart 3, right? So we've also used Chan to do the analysis. And from what Chan is giving, this particular profile, when you read the paper, the profile of the water oil ratio derivative is showing a natural encroachment. That is what you are seeing here. You don't see the curve down and the one up, but rather you just see a chart like a blunt profile. So that is showing a natural encroachment profile. I just said I should add all these ones so that we can see what we are talking about. Then look at this second chart. This second chart shows water into the well bore, then if you plot this, the churn plot, you see that initially it was going down, the curve was going down, just like we saw on the chart from Chan. So initially it was coning, then later it became natural encroachment from the interpretation. Then there is something I need to tell you. I talked about noise before now. So if you look at this one, can you see this one? As soon as we started producing from this well, as soon as production started from this well, right? As soon as production started from this well, you see water coming. So you see channeling, you see it going up, right? Then later, if you look at the well performance chart, all of a sudden it rose as if it was channeling. But the churn plot is still showing it as if it is natural encroachment. So why I brought out this is to also warn you that even as you use the chart to characterize your water, you also need to be aware of noise, right? So it's not something that you just pick only it. You need to write on the mechanism. And at the end of the day, you will still need to you need a way to confirm by either saturation logging, or if you can afford PLT, you do it. Just to a well, the top interval, right? Then you have a well where the water drops into the hydrocyclone and oil rises through it and fills the well, but the water goes into the lower formation. So you can do that downhole water separation. Then for wells that are still producing, that you still cannot do much about.
So, sorry, Mr. Hyacinth, you're breaking again. Mr. Hyacinth, can you hear me?
On the
Mr. Hyacinth, are you still with us? Apologies for that. I think he's having some challenges, so seems to have been his screen has stopped sharing. But yeah, we'll just give him a minute or two to rejoin. Yes, Mr. Hessing, can you hear us now?
Hello? Yes, I can hear you. Sorry about that.
No worries.
So when did you guys
Yeah, I think it was on your slide for water management, just after you were talking about the
for water
downhole
management?
separation and injection. That was where you were, locked
Oh,
out, I think. Yes.
okay. Please
Yes,
confirm you can
yes.
see my screen now. Thank you. Let me go to slideshow. Okay. Was it here?
Yes. So just
Okay.
before, as you were about to start talking about choke management, we lost it
Oh,
there.
so
Yeah.
sorry, but that was a long time ago then. Okay. So choke management, if you look at the water production mechanism, some of them respond to choke management, like coning, for instance. If your well is coning and you bend down a bit, if you bend down a bit, it will the water production will recede because you are no longer pulling so high. You know, coning has to do with viscous forces overcoming gravity. So as you stop pulling so high, then coning will recede. And how do you stop pulling hard? Is by binning down, right? So you reduce what you are pulling from the reservoir so it could respond. So choke management is a way that you can actually use to manage some water production. Then water shut off. So what I was saying was, as you are doing your well review, I hope you can still hear me, Gerard.
Yes, we can.
Okay, I'll be asking so that if anything happens, at least I will know early. So when you are reviewing a well that is producing at very high water cuts, you are looking at, like I said, you look at logs, you look at different maps, you look at different things, right? And you are asking yourself, based on the perforation depth and the top of the reservoir, do I have opportunity to shut off some of those perforations that are producing water and perforate shallower, right? So if that is possible, you can go carry out water shut off on that interval, then reperforate shallower. That may reduce your water production. But this water shut off, that is also why when you are completing your well, you need to be careful, because if the water is on short, if the water production is from a well that was completed with gravel pack, then it makes water shut off very difficult, right? But if it was completed maybe without sand control mechanism or SCON, sand consolidation, for instance, it becomes easier to shut off water. But what I'm saying is you can reperforate shallower and shut off water from the same sand. Then if you cannot shut off water from the same sand, are there shallower reservoirs? Or even are there shallower reservoirs that you can recomplete on? And if well configuration will not allow you to complete below the packer, to recomplete the well below the packer, is there opportunity above the packer where you can do what we call cement packer? So cement packer is just fill your tubing casing annulus with cement, right, up to a certain level, then perforate through the tubing, the cement, and the casing into a different zone. Then you can now produce from that zone and produce drier oil. So you can do this to manage your water production. I hope that is okay. You heard me.
Yes, we did.
Okay, thank you. So I'll just conclude because we've gone far. We've spent a lot more time than was planned. So in conclusion, I would say we've looked at production technology, and my hope is that you understand the discipline and you also understand the discipline holds. Then we've also discussed well performance analysis and common well problems. And like I said, your well problems, your well challenges are actually opportunities. And the integrated team works to make sure that we turn those challenges into opportunities. As you can see from this picture that you are seeing, so it's everybody's effort channeled towards recovering the most from our production system. Thank you very much. There are other slides, but time has gone, so I'll just stop here. Thank you.
Thank you very much, Mr. Hyacinth, for that fantastic presentation. The network tried to deter us, but we were able to forge through, and yeah, it's been it's been an amazing session. Can we please give a virtual round of applause, please, for Mr. Hyacinth, for that very fantastic presentation. I'm sure we've all learned a whole lot, from all he said. I will still open the floor for questions, but on that note, we will end the live stream, and we invite anyone who has joined us online to join us next week when we have our session on petroleum economics to wrap up the bootcamp. So thank you again, Mr. Hyacinth, for that presentation. I will end the live stream now, and then I open the floor.
We'd like to take some questions or contributions.
Yes. So we